Alex Eagles is a student technical team established in 2013, and since then we have participated in various international aerospace competitions representing Alexandria University. This year we will be participating in SUAS for the first time ever. Our development team consists of 33 members from a range of engineering disciplines led by Ahmed Bahieldin. The team is divided into 3 sub-teams: mechanical team led by Yahya Husayn that has been on the team for 2 years, electrical team that is divided into software and hardware sub-teams, both led by Yousef. Finally, Yousef Ghali, the electromechanical integration lead. Now we will introduce our competition team that is going to carry out the mission. Peter Ayoub, the safety pilot, Mazen Aser, the GCS operator, Nurhan Anwar and Omar Mitwalli, our software engineers, Ibrahim Hamouda and Ahmed Hani, our hardware engineers, Muhammad Fathallah, the airdrop coordinator. This year we have decided to take on a new challenge and build a fully autonomous drone that is fit to compete in the SUAS competition. Acceptance criteria. The mission demonstration simulates a search, delivery and rescue operation graded as follows: 10% timeline, 30% operators, 50% airdrop, and 10% operational excellence. For successful mission demonstration, our UAS needs to complete the given mission in less than 30 minutes. We have set the time limit to be 25 minutes to account for unexpected events. The 25 minutes are split into 18 minutes of cruising, 5 minutes of hovering for payload delivery, 2 minutes for takeoff and landing. And therefore, we have designed our system to have an average speed of 40 miles per hour in order to complete the 15-mile course in 25 minutes, with 5 minutes to spare as a safety margin. Also, the batteries must not get under 20% state of charge. Our UAS must be capable of obstacle avoidance and must remain inside the designated flight boundary. It also has object detection and payload delivery capabilities, which are all conducted autonomously. Raven, our first ever quadrotor UAV, is made out of locally manufactured carbon fiber tubes and sheets due to its high strength and minimal weight. Our UAV has 4 motors coupled to a 30.5-inch propellers. Raven is powered by 4 6S 28Ah lithium-ion NMC semi-solid-state batteries. A smaller 7.2Ah battery and a custom-made PCB were used to power the auxiliary system, as well as the dropping mechanism servo motors. To achieve autonomous flight, we used an Orange Cube Pix Hawk flight controller and here 3 GPS for positioning. Here link for RC control. Here link Wi-Fi is used in linking the ground control station with the Jetson Nano, our onboard computer. For the imaging system, we use the SIYI A8 Mini, which is connected to the Jetson Nano. Together, they are used for object detection, classification, and localization. Our communication link is split into 3 frequencies: 900 MHz, 2.4 GHz, and 5 GHz. Our dropping mechanism was designed to achieve high precision and speed while maintaining simplicity and reliability. Imaging and ODLC. For our imaging system, we chose the SIYI A8 Mini camera for several compelling reasons. It weighs only 95 grams and supports high-resolution video capture at 1920 by 1080 pixels, 30 frames per second, and a 6x digital zoom capability delivering sharp and smooth footage. It has a 1x1.7-inch image sensor and offers a wide field of view of 93 degrees, enhancing the overall visual coverage. Based on our calculations using the focal length, numerical aperture, and sensor size, we have determined that the objects will appear clearly within the required range. Additionally, the SIYI 8 Mini camera features a built-in gimbal compatible with Autopilot, providing excellent stabilization for smooth and steady shots. We also compared between multiple cameras such as the Raspberry Pi HQ camera and SIYI ZR10. During the development phase, our initial approach involved using an Arduino microcontroller and MPU 6050 sensor running a Kalman filter algorithm. This method was designed to process sensor data efficiently and maintain stable camera positioning through advanced filtering techniques. Another method we considered utilized the Pixhawk's built-in IMU data and applied a low-pass filter for smoothing. However, after careful consideration and testing, we decided to use the A8 Mini's built-in gimbal. This decision was based on a variety of factors including efficiency, reliability, simplicity, weight, and overall performance. To train our models effectively, each was trained on a different dataset. For our color classification model, a dataset of 40,000 RGB color ranges was extracted for the targeted colors using a custom software. The dataset's accuracy was validated using a custom tool where each sample was visualized and inspected. Additionally, we developed a custom dataset generator which we used to generate 18,000 images. This involved generating random backgrounds, overlaying shapes, and adding alphanumerics on top of them. We applied blur effects to those shapes to make them look realistic. Furthermore, we utilized the MetaSam model to automate the annotation process for the image segmentation. For our shape detection and classification model, 20,000 images were gathered and filtered. The dataset includes the shapes of circles, semicircles, quarter circles, triangles, rectangles, pentagons, stars, and crosses, beside human mannequins. These images had a resolution of 640 by 640 pixels and included annotations for each shape. As for our alphanumeric classification model, we cropped the shapes from our primary dataset utilized for the shape classification model. Due to the presence of multiple shapes in some images, we were able to gather nearly 37,000 individual shapes to train the model. After preparing our datasets, we developed a custom software to annotate our datasets. This software is capable of annotating the colors and alphanumerics simultaneously. General ODLC pipeline. The flowchart displayed shows how the recognition ODLC system works. In order to detect and classify the shapes, the YOLO V8 was chosen for this purpose. This choice was considered after training and testing different YOLO models. After training, we evaluated each model's performance and accuracy, and V8 gave the highest accuracy and minimum inference time. Upon shape detection, the shape is cropped from the image to concurrently classify the alphanumeric and the color of the shape and the alphanumeric. This approach is executed using multi-threading to minimize processing time. YOLO V8 is employed again for alphanumeric classification. During the selection process, YOLO V8 was benchmarked against models like ResNet 50 and Inception V3. Comparison metrics included training and validation curves as well as inference time, ultimately validating YOLO V8's superiority for alphanumeric classification. Before color classification, a UNet model segments the shape and the alphanumeric character from the background. K-means clustering algorithm is then used for extracting dominant colors with k equal 2 to get the clusters of shape and alphanumeric separately. A machine learning model trained with 40k RGB values that we made is then used to find the corresponding colors obtained from the k-means clustering. Localization was achieved using the camera and the GPS module. The target's longitude and latitude were obtained by measuring the target's distance in pixels from the image's center. Using the camera's 21mm focal length, we were able to convert this distance into meters and then into GPS coordinates. Airdrop design and testing. After conducting tests on several dropping mechanisms, a servo braking mechanism was used due to its lightweight and simplicity. A custom servo arm was designed. One side is responsible for holding the pulley in place during flight, and the other side is used to brake the falling water bottle to ensure smooth landing. Communication design and testing. Our communication system consists of 3 links: a telemetry link using RFD900X, a Wi-Fi link, and an RC link using the HERE link, as shown in our communication diagram. The telemetry link, which is a high-performance 900 MHz radio modem with a 40-km range, it enables data transfer between the ground control station and the UAV, which is achieved using MAVLink, a lightweight messaging protocol. The second communication link is the Wi-Fi link. For the Wi-Fi link, we have 2 methods that we can choose from. The first method consists of the HereLink Air unit and the HereLink Ground unit and is used for communicating between the Jetson Nano and the GCS to transfer images, data, and to control the mission from the GCS. This link is done by connecting the Air unit to the Jetson Nano via Ethernet port. The second method is done by connecting both the ground control station and the Jetson Nano to the same virtual Ethernet networking service, such as Zero Tier. This approach ensures that the GCS and the Jetson Nano are part of a secure and encrypted virtual network over the internet, enabling the Jetson Nano to transmit data, images, and receive commands from the GCS. The third link is the RC link of the HERE link. The HERE link uses a 2.4 GHz frequency band and has a range up to 40 km with latency as low as 110 milliseconds. It's used by the safety pilot in case of emergency. Alternatives considered. We considered using the Ubiquiti Bullet AC on the drone side and the Ubiquiti Nano Station AC on the ground control station for the Wi-Fi link, but found some complications as in the need of installing an antenna tracker on the GCS side, so we decided to use the HERE link as it surpasses in all aspects in establishing a stable Wi-Fi link. For Raven's frame, we used carbon fiber as it provided high strength while keeping weight at a minimum. We manufactured our own carbon fiber sheets and tubes with the help of professionals at our local shipyard. For our propulsion system design, we used performance analysis and constraint analysis to determine the most optimal drive configuration for our UAV. We chose T-Motors P80 III 120 kV motors coupled to 30.5-inch propellers and Alpha 80 ampere ESCs. This configuration provides us with a maximum of 72 kg of thrust, which allows us to achieve the required thrust-to-weight ratio. For the batteries, we use the 46S 28 ampere-hour batteries. We connected each two in series and then two in parallel, providing us with a maximum capacity of 56 ampere-hour. Batteries are mounted on the landing gear for stability and to provide enough space for our system. For our autopilot, we chose the Cube Orange Plus. The Cube Orange is equipped with high-performance H7 processor, which provides high-performance and stable solution for flight. It's also equipped with real-time triple redundant temperature-stabilized IMU system, which provides backups if errors occur, enhancing safety and reliability. To accomplish our mission autonomously, we developed a custom navigation software using the DroneKit API. While the vehicle is on the ground, our custom navigation software starts by planning the navigation path to ensure moving in the shortest path possible between each two waypoints. After that, the software sends the necessary commands to the Pixhawk to initiate a safe takeoff. After taking off safely, the software sends the necessary commands to the Pixhawk to complete one lap across the waypoints and then head to the survey area. Our team carefully evaluated multiple sensor options. Ultimately, we selected the Lightwear SF45B LiDAR. It's lightweight, robust, and possesses an impressive 50-meter range in bright sunlight conditions. Additionally, the SF45B integrates seamlessly with ArduPilot. ArduPilot's obstacle avoidance functionality employs a hybrid approach, utilizing the bendy ruler algorithm. For local path planning to navigate around proximity-based obstacles, while globally rerouting via Dijkstra's algorithm to identify the shortest collision-free path around geofenced areas. We considered the RP LiDAR A2M8 for its 360 range and easy ArduPilot integration, but we rejected it due to its poor performance in direct sunlight and its low detection range on 8 meters. Due to strict regulations on drones in Egypt and difficulties faced while trying to obtain flight permits, simulation has played a vital role in refining our capabilities. Simulation environments like Gazebo and SITL software in the loop to perfect our drone's mission execution. These tools provide a cost-effective and legal way to test and validate drone functionalities without the expense and risks associated with real-world testing. This is particularly crucial in early development stages. Simulations allow us to replicate a wide range of scenarios and environmental conditions that might be challenging or rare to encounter in real life. This helps in understanding how the drone will perform under various circumstances. We also used simulations for integration testing of the navigation system with the ODLC system. This ensures that all components work seamlessly together before actual deployment, minimizing potential issues during the mission execution. By leveraging simulation tools effectively, we can enhance the reliability, efficiency, and safety of our drone operations, ensuring that they meet the demands of complex missions and environments. Due to the team's previous experience, we were inclined to design a fixed wing or a VTOL, but after conducting trait studies, we decided to switch to a rotorcraft approach due to the inadequate turning radius and low airdrop accuracy of the fixed wing and the VTOL. We then compared between a hexacopter design and a quadcopter design and decided to go for the quadcopter as it provided similar flight times at significantly less weight than the hexacopter design. Preparing for a successful mission means mitigating potential risks. Here's how we've addressed them. To combat mechanical or electrical failure, we've created checklists and safety protocols for setup and manufacturing. Additionally, we've constructed a test drone specifically designed to rigorously test all systems before actual deployment, ensuring thorough testing and reliability. Telemetry or RC loss is minimized through rigorous ground testing and the use of backup systems. Structural integrity is ensured through thorough stress analysis and finite element analysis of our aircraft frame. Navigation reliability is guaranteed with full mission simulations to verify accuracy before deployment. Operator safety is paramount with mandatory safety gear worn during all phases. With these measures in place, our mission is set up for success. We evaluated our models on a customized dataset, which was a very challenging dataset, and it's not available for public release. Our shape detection model was tested on a test set of 220 samples, achieving a classification accuracy of 96.82%, a precision of 0.9, and a recall of 0.96. As for our alphanumeric classification model, it achieved a classification accuracy of 95%. While the color classification model was tested on 1,726 samples successfully, classifying 95% of the shape's colors correctly and correctly classified 78% of the alphanumeric colors. Our flight termination system is triggered upon completing the mission or in the event of a lost communication link. It initiates automatically after the autopilot receives a termination signal. Once activated, the flight termination system executes the necessary procedures to transition the vehicle to a low energy state, ensuring a safe landing at the designated termination point. We have made significant efforts to strategically place components taking into account factors such as environmental influences and potential sources of interference. In order to optimize performance and minimize external impacts, our Pixhawk flight controller is positioned at the center of gravity of the drone, which is crucial for stable flight. Secondly, by keeping it away from the batteries, we minimize the electromagnetic interference, safeguarding the Pixhawk's functionality. For the HearLink antennas, we've made a deliberate choice to mount them on a non-conductive material to prevent interference with signal transmission, affecting range and performance. Additionally, we've oriented the antennas vertically with a 15-degree rotation. This optimized alignment enhanced signal reception and transmission, ensuring a reliable communication with the drone. The RFD900X telemetry is placed far away from the carbon fiber to avoid distortions to resonant frequency, gain, and radiation pattern, which can impact performance. By carefully considering the placement of these critical components, we've optimized our drone for peak performance and reliability, ensuring every flight is a success. We have positioned the GPS module to maintain a clear line of sight, ensuring accurate positioning data. Additionally, we shielded it from the electromagnetic interference by keeping it away from the motors and batteries. We have positioned the LiDAR at a height above the GPS module to provide an unobstructed view of the surroundings for accurate distance measurement and obstacle detection. Securely mounting it to minimize vibrations and potential misalignment is also essential for reliable performance.
Flight Readiness Review. We have faced major issues in importing the batteries required for our UAV due to strict regulations on drones in Egypt, and therefore we were not able to conduct flight tests. We have tested all our systems using our small-scale test drone. We have also tested our propulsion system using AC to DC converters as shown in the video.
The journey to create Raven, our cutting-edge autonomous drone, has been a remarkable experience marked by teamwork, dedication, and innovation. At Alex Eagles, we believe in the power of collaboration, and Raven is the product of a year-long collective effort that brought together diverse talents and expertise. Raven represents the best of our teamwork, combining AI-driven object detection, classification, and localization to achieve precise payload delivery. Every member of our team played a crucial role in the development process, from designing the drone's hardware to refining its software algorithms. We held countless brainstorming sessions, prototyping stages, and test flights to ensure Raven met our high standards.